Hello, everyone. Today we're going to talk about what is called the standard normal distribution. Hi. By definition, if a continuous random variable has a distribution with a graph that can be described by the following equation, we say that it has a normal distribution. A normal distribution is bell-shaped and symmetric. The equation below is our equation of a normal distribution. We're not going to focus too much on this equation at all, but we want to note this bell-shaped curve in the top. Notice we have the mean value in the middle, a symmetric curve, and that is going to be what we think of when we start thinking about normal distribution. So normal distribution, bell-shaped curve, that's the connection we want to make. Let's continue with some definitions. A continuous random variable has a uniform distribution if its values are equally spread over the range of possible values. The graph of a uniform distribution would just be a rectangle, which makes sense. If everything's about the same, remember our histograms, they'd all be the same. Same thing for a curve. It'd be a rectangle. All the values are the same. The graph of any continuous probability distribution is called a density curve, and the total area would be 1. So under the curve, it's always equal to 1. So that's a good way to check things if we need to. And since the total area under and density curve is equal to 1, there's a correspondence between area and probability. So basically what we're going to do is we're going to take the geometry of the curve that we're dealing with, use the geometry to figure out what the area is under the curve, and then since there's a correspondence, we can take whatever that area is and then also determine that that is the probability. All right. Let's look at an example. If we have waiting times for airport security, during certain time periods at JFK in New York, passengers arriving at the security checkpoint have waiting times that are uniformly distributed between 0 and 5 minutes. So clearly this is not true. It's probably between 0 and 2 hours, but if we assume it's between 0 and 5 minutes, all of the different waiting times are equally likely. Waiting times can have any value between 0 to 5. If we assign the probability of 0.2 to the height of the vertical line, it would create an area of 1. So since we know that the area has to be equal to 1, it's uniformly distributed, so the probability has to be the same for everything. And then if I have 5 possible choices, 0, 1, 2, 3, 4, 5, I break it up 1 divided by 5, which would be 0.2. So that's how we can use this area equaling 1 to help us figure out what the probability should be. It's a little easier with the rectangle. Later on, we'll see some other ways we can do this if we have to use a different shape. And this is a way that we can apply it. Let's say we want to find the probability of a wait time of at least 2 minutes. So since we know it's a rectangle, it's always height times width or length times width. Call it height here. And we know that the height has to be 0.2 because the rectangle, we said the probability of everything is 0.2. So the height of that rectangle is 0.2. And then there's 3 possible choices. It could be 2 to 3 minutes, 3 to 4 minutes, or 4 to 5. So, or you can think of it as the difference between 5 and 2 would be 3. So one side has length of, or height of 0.2. This has a side length of 3. 0.2 times 3 is equal to our 0.6 here. Right. So the standard normal distribution. This is what we're going to mostly focus on because for a lot of our statistics tests, we need to assume that we have a normal distribution. So when we say that, this is what we are referring to. So we say the distribution is a normal distribution so that it is a bell-shaped distribution. The population parameter of the mean has the specific value of mu is equal to 0. The population parameter of standard deviation is 1, and then the total area under the density curve would then be equal to 1. So under this bell-shaped curve, our area is still equal to 1. It is a little bit harder to see since it's not just a rectangle, but it will still have an area of 1. And we're going to find probabilities now with given z-scores. And we're going to be able to use this curve to actually figure this out. And just note real quick, on our distribution, this horizontal axis are z-scores still. So if 0 is the mean, and standard deviation is 1, 1 is 1 standard deviation, 2 is two standard deviations. So we're able to connect probability to our z-score, because remember that a z-score is how many standard deviations we are away from the mean. So with that in mind, let's look at an example. So we have a bone mineral density test can be helpful in identifying the presence or susceptibility of osteoporosis, a disease that causes bones to become more fragile and more likely to break. The result of a bone density test is commonly measured with a z-score. The population of z-scores is normally distributed. We have this key piece here with a mean of 0, standard deviation of 1, which, since it's normally distributed, we can imply that. So these test results meet the requirements of a standard normal distribution, and the graph of the bone density test scores is shown next. A randomly selected adult undergoes a bone density test. Find the probability that this person has a bone density score of less than 1.27. All right. So what we're going to do to find this probability now is we're going to use the standard normal distribution, since we can see there is a correspondence. So let's take a look at how this would work. So here's what we have, which is known as a z-table sometimes, or the standard normal distribution table. I a lot of times just call it a z-score table. But on the left side, we have all these potential z-scores. So 0 to 1.9. So that's the vertical column. And then the row is 0.00 to 0.09 is the 100th digit. So going back to the question, we want 1.27. So we're able to read our z-score table. We want 1.2. Those are our first two digits, right, in 1.27. And then we want our 100th digit, which is 0.07. And then we line it up. So this would go to here. We line it up. And we can now see our probability. So our probability would be 0.89796. So it's very important to note here that these table values represent area left of the z-score. So since we are assuming we want to find the probability that a person has a bone density less than, we're actually done. Since this tells us to the left, this is going to tell us the area to the left or the probability to the left. So we matched up the number, we got 89.796%. Right. So here's another representation of it if we draw it out. So the probability that a randomly selected person has a bone density test result below of 1.27 is this number we just saw on the table. It's just rounded here, same exact value. If we go back, we're just rounding that 7 to an 8. Same number. And again, it will tell you on homework or something like that how many decimal places we want to round to for probability. But it's rounded to 0.8980, and it's shown in the shaded region below. Another way to interpret this is 89.8% of people have bone density levels below 1.27. So we're able to find that value in the table, whatever that probability is, or z-score, probability of that z-score. Since we have the correspondence between area and probability, we're able to find the probability just by looking at the table. If we wanted to know more then, we'll have to do a little bit more work, but we'll see that in a second. And this table can be found on Canvas. You can also just Google it. If you search z-score table, a million different versions of it will show up, but I will post a copy on Canvas as well. So let's look at another example here. So same problem, we're still dealing with the bone density, but like I said, we're going to look at above now. So we're using the same bone density test from before. We want to find the probability that a randomly selected person has a result above -1. So the z-score is -1. We want to know above -1 this time. So we still want to find the value of -1. So this would be -1. Z-scores, remember, can be positive or negative. I just posted the part of the chart that was helpful. The real chart normally is double-sided with the negative side and the positive side. But -1, and then we know the decimal place is 0, so it would be the first one in the column. So this would be a top 0.00. So our probability is 0.15866. But since the question says above -1, we aren't done yet. We have to subtract this probability because this is the probability to the left. We want the probability to the right. We want more than. So we can see this a little better on this graph here. So if the area from the left is the following, so this is what we noticed on our chart, z equals -1, probability is 1587. Since the area is 1, which is a very nice property, we can subtract this number from 1 to find the right. So on the left side, we have this probability, and then we do 1 minus to find the probability over here. So to summarize, the probability to have more than a -1 z-score for bone density would be about 84.13%. So we saw less than, we saw greater than. We could also use this chart to find between two values. So I have a lower bound and an upper bound. So a bone density reading between -1 and -2.5 indicates that the subject has osteopenia, which is some bone loss. Let's find the probability that a randomly selected subject has a reading between -1 and -2.5. Okay. So I'm going to give you our z-scores here. I want you to do this yourself, use the chart, and double check these values. Z equals -1, we just saw, that's the one we did on the last slide, is -1.587. And then double check, z equals -2.5 on the chart would be -0062. So whenever we want the probability between two, all we have to do is subtract the probabilities. So in summary, we know that the probability to the left is this minus 0.587 of z equals -1, for z equals -2.5, it's less than 1%. And then what we're going to do is we subtract those values. So I'm doing 0.1587 minus 0.0062. And then that's where we're finding this number here. So 0.1525. So two values, find the z-scores on the chart, find those probabilities, and then you can go ahead and subtract them. This isn't the only way to find z-scores. I'll allow you to use technology to find z-scores if you choose so. You can do it on your calculator. It should tell you the z-scores if you set it in statistics mode. There's a million z-score calculators just on Google, so you're welcome to use those or use the chart. The chart's just straightforward and easy to read. And now let's talk about critical values. So for the standard distribution, a critical value is a z-score on the borderline separating those z-scores that are significantly high or low. We commonly just remember these critical values of z equals negative 1.96, positive and negative, since only 5% of the population have scores above and below 2.5% each. We can check these values on our z-score charts. I think I put one in. Yep. So we have 1.96 we'll look at. 1.96 would be right here. 0.975. So that means the probability is 97.5% that it's going to be to the left. So to the right, if I do 1 minus this number, it's 0.25, which we can also just think of as 2.5%. And that's just on the positive side. If we do the same thing for the negative, it'll be the other 2.5%. So that means it's falling in between 2.5% on the right, 2.5% on the left. We can find it here as well. So we want negative 9.6. Should I count that right? 1, 2, 3, 4, 5, 6. Yep. So here's our other 2.5%. So remember, it's another way I could see this is if I subtract these to get two values, my two circled value, 0.975 minus 0.025 should be 0.95, 95% of the data. Right. So that is going to be it for today's lesson. So take some practice using the z-score table, and I will see everyone next time where we talk about some applications of normal distributions.